Okay, so I'm going to record some examples. These are the examples from the Pear Deck. So if you want to go through and practice those, I'm going to go through how to draw the Lewis structures for each of these on this recording. So I'm going to start with N to F2. That's the first one on the recording. I always start by calculating the total number of electrons. So this is N to F2. So my total electrons, and I find that from the periodic table by figuring out how many valence electrons each atom has and adding them all up together. So for this molecule, I've got 5 from each nitrogen, and then I've got 7 from each hydrogen. And remember, that just comes from how many valence electrons that each of those atoms has. So altogether, this gives me 5 plus 5 is 10 plus 14, 24 electrons. So I always start by finding my total number of electrons. Then I draw my skeletal structure by deciding which atoms are in the center. In this case, I've got 2 of each, so there's not really a central atom. So I'll put both my nitrogens in the inside and both my fluorines on the outside. So this is going to be N, F, and F. You could also draw this like this. Whoops. That would be fine too. But I'm going to go with the one on the left, just because for me it's a little easier to look at. So then from here, when I have my skeletal structure, the next step is always to figure out how many remaining electrons do I have. So I had 24 total, and now I have 2 in this bond, 2 in this bond, and 2 in this bond. So remaining, I have 24 minus 6. So I have 18 left. That means I can put 18 electrons around these atoms. So I'm going to put 2, 4, 6, 8, 10, 12, 14, 16, and 18. My next step is then to determine if I have all my octets satisfied. And if I do, I'm done. And if I don't, then I need to fix something so that everybody has a full octet. So my fluorine has 2, 4, 6, 8 atoms around it. So it's happy. My other fluorine, 2, 4, 6, 8. This nitrogen, 2, 4, 6, 8. But this nitrogen has 2, 4, 6 atoms around it. So this nitrogen is not satisfied. So what I need to do is I need to take 2 of the electrons from here and put them into a bond and say, okay, you know what? I don't need them all to myself. We can share them. So what this is going to end up looking like is we're going to take these 2 electrons off and we're going to turn them into a bond. We're going to say instead this has a double bond. So then now this guy also has 2, 4, 6, 8. And then I just want to double check. I didn't make up any electrons, right? I started with 24. I should still have 24. So I'm going to count everybody up now that they all have octets satisfied. And I want to make sure I didn't create any electrons from nowhere. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So as long as I have the same amount of electrons I started with and everybody has a full octet, then I've got a valid structure. All right, let's look at the next one. The next one is CH2. So I start by calculating my total electrons, which is going to be equal in this case to 6 because sulfur has 6 valence, plus 4 because carbon has 4 valence, plus 1 from each of those hydrogens. So altogether, I've got 12 valence electrons here. Now, when I give you a structure like this, I'm going to tell you what the central atom is. I can't remember if I did on the Pear Deck or not, but if I gave you one like this on an exam, I would always tell you what the central atom is. Okay, I don't have it anywhere. But in this molecule, carbon is going to be my central atom. So I'm going to draw my skeletal structure. I'm going to draw an S on it, an H on it, and an H on it. So you guys wouldn't know without me telling you what goes in the middle. So I would tell you carbon is the central atom here. Okay, so I have my skeletal structure. Next, I want to find my remaining electrons. So that's going to be the 12 I started with minus the ones that are taken up in these bonds. So I have 2, 4, and 6. So I have the 12 I started with minus the 6 in bonds, so I have 6 remaining. That means I can put 6 electrons around everything else that's on here. I'm never going to put them on my hydrogens because hydrogen doesn't want any more electrons. So I'm going to do 2, 4, and 6. You could also put 2 on the carbon instead. Doesn't matter. But then finally, I need to figure out, okay, are my octets satisfied? So for sulfur, 2, 4, 6, 8, sulfur's happy. Hydrogen only wants 2. Hydrogen wants 2. But this carbon has 6 electrons around it. So it doesn't have a full octet. So what I need to do, I can't erase my sad face. What I need to do is I need to take 2 of these electrons. I'm going to take these ones just so my image stays symmetrical. And I'm going to share them with carbon. So these 2 electrons are going to get turned into a bond. So I'm going to take them away from sulfur. Sulfur says, you know what? We can actually share them. Let's put them right here. So now those 2 electrons that were here, instead they're in that bond. So now sulfur still has 2, 4, 6, 8, but now carbon also has 2, 4, 6, 8. So now everybody's octets are satisfied, and I have to make sure, do I have the same number of electrons that I started with? So I add them all up. I have 2, 4 lone pairs, and then 2, 4, 6, 8 from my bonds. So I have 4 in my lone pairs, 8 in my bonds. That's 12 altogether. All right. Next example we have is PBr3. I may not go through all of these, but I do want to go through quite a few for you to be able to see. You can skip ahead in this video if you are like, oh, I totally got that one. I don't need to worry about it. Or just look at the answers as you go through to check yourself. But I do want to go through them all the way. So feel free to skip around as you need to. All right, so next we've got PBr3. So I start by finding my total electrons. Phosphorus has, let me look at my periodic table. Phosphorus has 5 valence electrons. And then each bromine has 7 valence electrons. So I'm going to add 7, 7, and 7. Altogether, this gives me 26 electrons. So in this case, it's easy to find my central atom because it's the one there's only one of. So I'm going to put my phosphorus in the center and my bromines around it. Again, if you draw it slightly differently, this is okay. If you want to draw it with one of the BRs on top, this is fine. As long as you have a bromine only in one of these 4 spots. Drawing them at kind of an angle would be wrong, but putting them, whichever one of those slots you leave empty is fine. Okay, so then I figure out I have my skeletal structure. Next is to find my remaining electrons. So my remaining electrons are the amount I started with minus the amount that are in bonds. In this case, it's 3 bonds, so 2, 4, 6 electrons are in bonds. So I have 20 left that I can draw as lone pairs. So I'm going to go ahead and fill in those 20 electrons in pairs around my other atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Then I check if everyone's octets are satisfied. So I've got 2, 4, 6, and then 2 in the bonds for this bromine, 2, 4, 6 from the lone pairs, and then 2 from the bond. So that's 8 for this bromine, 2, 4, 6, 8 for this bromine. And then each bond has 2 for this phosphorus plus the 2 in the lone pairs. So this has 8 as well. So in this structure, I don't have to move anything around. I don't have to create any double bonds. I've got all of my octets satisfied. I'm going to go ahead and double check. Did I hit 26? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. So I didn't make anything up. So my 2 requirements are met. I have all my octets and I have the same number of electrons that I started with. That's always what we're looking for our lowest structures. All right, so this is PBr3. Next, we're going to go on to O2. Like I said, skip around as you need to. You don't have to watch every one of these examples, just as many as you need to get the hang of it. So my total electrons in oxygen, I have 2 oxygen atoms. Each oxygen atom has 6 valence electrons. So altogether I have 12 electrons for this structure. There's no central atom here because I've just got 2 of the same thing. So my skeletal structure is just going to look like this. Then I ask myself how many electrons are remaining. So I'm going to subtract the total I start with. So I have 12 altogether minus how many are used up in bonds. In this case, I've just got 1 bond. So I've got 2 electrons in there. So that means I have 10 left. So I'm going to put those 10 electrons, I put my remaining electrons around my other atoms. 2, 4, 6, 8, and 10. Then I see which atoms are or are not satisfied. So the oxygen on the left has 2, 4, 6, 8, so it's happy, but the oxygen on the right, 2, 4, and 6. It's missing. It really wants 2 more electrons. So the oxygen on the left says, oh, I'm so generous. We can actually both use these. These are going to become bonding electrons. So we're going to ditch these and we're going to turn it into a bond. We're going to share that pair. Oops. So then I check, is every atom happy? 2, 4, 6, 8 on this oxygen. This is good. 2, 4, 6, 8 on the oxygen on the right. And then all together, 2, 4, 6, 8, 10, 12 electrons all together, just like we started with. All right, next example we have is SF2. So again, my first step, pause here, try a couple of these, try the rest of them, see if you're getting them right. So we've got total electrons is going to be equal to, in this case, I have 6 electrons from sulfur. Those are the amount of valence electrons from the periodic table, and then 7 from each fluorine. So that's going to be, let's see, 14 and 6. We're going to have 20 electrons altogether. To figure out my central atom here, I go for the atom that I only have 1 of, which in this case is sulfur. So I'm going to draw my S with my F's around it. If you want to draw them top and bottom, that's fine too. Then I calculate my remaining electrons equals the amount I started with minus the amount in bonds. I have 2 bonds. They both hold 2 electrons. So that's 4, which means I have 16 left. I'm going to place them around my other atoms. 2, 4, 6, 8, 10, 12, 14, 16. This one's pretty easy. It looks like I'm going to be done because everybody's octets are already satisfied, so I don't need to make any double bonds here. This one's good. I have 2, 4, 6, 8 around fluorine, 2, 4, 6, 8 around sulfur, 2, 4, 6, 8 around this fluorine. So all my octets are satisfied. And then count up all together, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20 altogether. So my octets are satisfied and I have the right total number. So I'm happy with SF2. All right, I think I actually will just go through all of them. But again, you don't have to watch them all. Feel free to skip around, watch the ones that you need help with, and then I'll put a picture at the end that has the solutions for each one. So if you just want to check your work, you can do it that way. All right, next we have C2H2. Oops, C2H2. So my total electrons here is going to be 4 from carbon plus 4 from my other carbon plus 1 from my 2 hydrogens. So I have 10 valence electrons that I can use in this structure. Here, I can't really figure out a central atom because I've just got 2 of each thing. So I just want to draw this in a way that's symmetrical and so that I'm not putting any weird extra stuff on hydrogens. Okay, so I'm going to draw it like this. I could also draw it like this if I want to. Either way is fine, but I like the way on the left better for this one. Sometimes I draw it the other way, doesn't really matter. So then I figure out my remaining is what I started with minus the amount of electrons in bonds. So I have 1, 2, 3 bonds. Each of those bonds is holding 2 electrons. So that means I've got 6 electrons that are used up in these bonds, which means that I only have 4 electrons left to place around my atoms. I'm not going to put any on hydrogen because hydrogen is happy and satisfied with only 2 electrons. So I'm going to put them all on, I could put them on both on the same carbon, or I could put them on the other carbons. I like to try and keep things as symmetrical as I can. So I'm going to put one on this carbon and one on that carbon. Okay, so my next step is to figure out, are my atoms happy? This guy only has 2, he's good. 2, he's good. But my carbons have 2, 4, 6, and 2, 4, 6. So my carbons are not satisfied. So what I'm going to do is I'm going to take these 2 electrons, and a carbon's going to say, you know what? We can share them. So these 2 electrons will turn into a bond here. Okay, but now I actually am still not satisfied. Now this carbon is happy because it's got 2, 4, 6, and 8. But this carbon is still not satisfied. It's only got 2, 4, 6. So I actually need to do that again. I need to say, all right, well, instead of my carbon on the left donating some electrons to this bond, let's let my carbon on the right donate some electrons to this bond. So now, just like my other carbon did, we're going to take these 2 electrons, and we're going to say, you know what, we can actually share these ones too. You contributed, I'll contribute too. So we're going to take those 2 electrons, and we're going to turn those into a bond as well. And now I'm going to count up because I did a lot of rearranging, so I want to make sure I still only have 10 electrons. I moved stuff around from lone pairs to bonds, but I don't think I made up any electrons, but I want to double check. So I have 2, 4, 6 in this triple bond here. That's 6 electrons. Plus I have the 2 here and the 2 here. So that's 6, 8, 10. So I have 10 electrons altogether, which is what we want. So we're good here. And then I have to make sure everybody is satisfied. So my hydrogen has 2 electrons. That's what we want. This hydrogen has 2 electrons. That's what it wants. This carbon has 8 electrons, 2, 4, 6, 8. And this carbon has 8 electrons, 2, 4, 6, and 8. So this is a good structure. Everybody's happy. All right, I've got one more neutral molecule, and then I've got a couple of polyatomic ion examples. So for my last neutral example, we are going to look at BeF2, and I crossed out number 7 because I accidentally gave you O2 twice. So if you want to see O2, skip back a little earlier in the video. We went through that one first. So I start by saying, how many total valence electrons do I have? So I look at my periodic table and I find beryllium has got, oh, you know what? This is actually an ionic compound. So I am going to skip this one because this should be ionic, because this is a metal and this is a non-metal. Metal, non-metal. So this is ionic. And we don't really use Lewis structures for ionic compounds. Since they form those crystal lattice structures, we would just kind of indicate it like this. And we've got 2 of these. So I'm going to cross this one out as well, actually, because this, we don't really draw Lewis structures for our ionic compounds. That's my bad. But we do draw Lewis structures for our polyatomic ions because our polyatomic ions are covalently bound to one another in order to form an overall charged molecule. Charged ion. So I've got CN1 minus is my first polyatomic ion I want to draw the structure for. So CN1 minus. The only thing that's different about these is when you're calculating your total electrons, you're going to have to take into account the fact that we have extra or fewer electrons based on whatever this charge is. So since this is 1 minus, that means I've got 1 extra electron as compared to if this was neutral. So when I'm adding up my total electrons, I'm just going to add plus 1 at the end because I've got 1 extra electron in here. So my total electrons equals the 4 from carbon plus the 5 from nitrogen. This would be a neutral CN compound, but I don't have a CN compound, I have a CN ion, so I've also got this 1 extra electron on here. Oops. Okay, just want to erase this so it looks nicer as we work. All right, so this is CN1 minus. Okay, so my first step is calculating my electrons, and the only thing that's different here is I added this 1 for my charge. Then I draw my skeletal structure. There's no way to draw a central atom here since I've only got 2 atoms involved. So I've got C and N. There's 1 bond in my skeletal structure, so my remaining equals what I started with minus the ones in bonds. So I've got 8 electrons left. I'm going to draw them around my other atoms, 2, 4, 6, and 8. And now I've got to make sure everybody has a full octet. In this case, my carbon does, but my nitrogen only has 4 electrons around it. So I need to draw some bonds. So I'm going to take these 2 electrons away, turn those into a bond. And that gives me still 8 electrons around carbon, but now I have 6 around nitrogen. So we're a little closer, but we're not all the way there. So carbon needs to loan out another 2 to share. So we're going to take these 2 off the bottom, and I'm going to turn those into a bond as well. So now I have the same number of electrons that I started with, 2, 4, 6, 8, 10, and carbon has an octet and nitrogen has an octet, so everybody's happy. All right, I've got 2 more polyatomic ion examples. Next is ClO3. So I've got chlorine and 3 oxygens here, and it has a 1 minus charge. So remember, this means I have 1 chlorine, 3 oxygens, and all together, this whole thing has a charge of 1 minus. So when I add up my total, I just have to add 1 extra electron because of this charge. So my total electrons equals 7 from chlorine, 6 from each oxygen, and then I have 1 extra because of the charge. This is my extra electron that's turning it from ClO3 as a neutral compound to ClO3 1 minus. So let's see, this is 6, 12, 18, 19, this is 26 altogether. My central atom, and now I want to actually just throw these parentheses on. I don't have to do this, but this is going to help me to remember. I don't care what this charge is anymore. I've taken it into account. I've considered it. I know what I have to do with it is just add this 1. So really, I just have to think about what's going on here. So my central atom is the atom that I only have 1 of. So it's going to be Cl. And then I draw my O's. You could also draw it with 1 up here instead of here, or however you want to draw it, as long as you've got 1 oxygen in each of those 4 slots and nowhere else. Okay, so I've got Cl and 3 O's. Now I have to figure out how many remaining electrons I have. So that's going to be the 26 I started with minus the ones that are in bonds. I've got 3 bonds. They each hold 2 electrons. So this is 20 electrons remaining. So I'm just going to draw them around my other atoms. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Would you look at that? We love it when that happens. We don't even have to figure out anything else because everybody's octets are satisfied. And then this is one step I forgot to do on the last one. We want to take our structure and put it in a bracket and just say this whole thing has a 1 minus charge. I forgot to do that on my CN. I should have done that. So I'll throw that in with this was my CN structure. And I should have put this into brackets and said this whole thing has a charge. All right, last example is OH1 minus my hydroxide ion. So I have OH1 minus, that is written down there below ClO3, you just can't see it, it's there. So OH, I start with total electrons. It's going to be 6 from the oxygen plus 1 from the hydrogen plus that extra electron that's turning this into a charged ion. So altogether that is 8 electrons. I draw my skeletal structure. Then I figure out how many remaining electrons do I have. I have the 8 I started with minus the 2 that are used up in this bond. So I've got 6 left. So I'm going to put them all on my oxygen because hydrogen really doesn't want any extra electrons. And again, would you look at that? We're already satisfied. So my oxygen has 2, 4, 6, 8. My hydrogen has 2. So these are both both have their full octet, or in the case of hydrogen, it's full duet. And I have 2, 4, 6, 8, which is what I started with. So last thing I want to do is just say, and also, by the way, this whole thing has a 1 minus charge. And that's all I've got to do to indicate this is an ion. All right, guys, so hopefully you were able to find these examples helpful. I went through all of the ones on the pair deck, so feel free to go back and review any that you need to. Go back and practice, try them on your own. These are just here to help you. All right, thanks. Have a great day.